魂トゥルビルダダトゥルダダ塊魂トゥルビルダダトゥルダダ素敵な君の顔見つめるほど I love you ゆるく晴れ渡る空魅惑のそのほっぺつねりたい Close to you so 風の中雲にふわり寝転んで観察ブランコの揺れる音あくびする坂道そうきに旅に出よう手をつなごう空の匂いはいろんな色模様アフロサスカイ渡る道は君への愛いつまでも終わらない夢君とやたら切ない朝曇り窓にシンゴビュー君の姿かたどる懐かしい足音が太陽くすぐるよマーサンシャイン笑おうたまにゆらり塊水たまり流れる風の匂い背伸びする校舎そうにもビュー夢のほとり固めたり風の気持ちはいろんな色模様遊ばい空の道は迷うことないどこまでも終わらない世界君と走り出す昔出会った道忘れてた蘇る遠い記憶が口笛吹いて通り過ぎる
Hello. Welcome back to Chem 140. What are we doing today? We are going to finish Unit 9, probably. And there's a cat. I just felt her brush against my elbow. Hi. Hi, you're a cat. I'm trying to... She had something in her eye. Hi. Do you want to say hi? Maya, do you want to say hi? No, she just wants to sit here. We're going to finish Unit 9. Agenda items. Quiz number 4 is due tonight. It will close 24 hours later. So make sure that you get that in by the deadline. And then we're also going to talk about lab worksheet number 3, which I need to get out of the modules tab real quick here. That's not what I meant to do. Hold on. I screwed it up. There, that's the one I want. All right, lab number 3 is pretty simple. It's going to have you watching a video that Samita made and I edited. So let me get this on the screen real quick. Yeah, that's the one I want. Boop. All right, so lab number 3 is all about ionic compounds, which we are studying right now conveniently, so it's relevant. It is very difficult to chemically identify ionic compounds because a lot of them are soluble in water and also very unreactive. So like, for example, sodium plus or potassium plus, very hard to study those effectively and identify them definitively. But we do have some methods. For example, if we set them on fire, the end result that we observe is that we get a color. And the colors differ depending on what ion is burned. And so you can see that in this picture of fireworks here. This is literally what we do with fireworks. We put elements into the rocket or whatever thing that we are going to propel into the sky. We set it on fire and it explodes. The metal ignites and you get pretty colors. That's cool and all. So I'm going to have you watch this video that's in this link. Samita made this video, and then I took it and shortened it down because I think it was like 45 minutes. I was like, Samita, no, that's not okay. My students aren't going to watch it for 15 minutes, which is what I think I shortened the video down to. And you're going to collect data from that as Samita does the flame test. Now, what I'm going to do is I'm going to actually put the video on the screen here. So I need to actually capture it. So hold on, let me see that I can get it here. If it loads here. There we go. Okay, so now I could do this. Yeah, that doesn't quite help, does it? All right. So this is the video that you're going to be watching for this experiment, the flame test. So this is Samita, who you can only tell that it's Samita because her name tag says Samita on her lab coat. But what she's going to be doing, and I've actually put some annotations in the video with some help for you. Buffering, of course. Thanks, video. You know what I should probably do? Let's see here. Where are my annotations? There you go. So I'm going to put stuff on the screen, kind of like what I did in my first video, that will help you to indicate stuff. And it's going to basically go through how does a Bunsen burner work and how does a conductivity probe work. And Samita's going to walk you through the directions on how to do that because I realized that nobody has one of these at home. You certainly aren't going to go to your kitchen and pull out your Bunsen burner. This isn't 1830 or whatever. Likewise, you don't have a conductivity probe because it's not 2765 or whatever year we would all need those to detect impurities in our water or something. I don't know. That got dark all of a sudden. But what we're going to do here is for the first experiment, we're going to light these samples of solutions on fire by vaporizing them. And so you could see that Samita is holding this watch glass with the solution on it right here. And what's going to happen is she's going to take a heated coil touch it to this, and it's going to get sucked up into the Bunsen burner. You're going to see a color. And I'm going to let her do that for an example here. So she's going to heat this up until it's white or red hot, not white hot. So you can see it's starting to glow. It's probably hot enough, so she's going to touch this to the solution. And what I think happens is the video should pause. I'm just waiting on her to actually do this. I know if I touch forward... Okay. There we go. Samita, please. There we go. All right. So you can see that the flame changed color. And she's going to do it again. And I believe that I paused the video for you. Yeah, there you go. Okay. So I paused the video even though it's still going. You can see the timer's going. So when you see a warning come up that says record your observations in your report form, pause the video and write down what you see. Because in the actual report form, you're going to be writing down the colors of the substances. Oops, sorry, that's the wrong page. You're going to write down the colors of the substances as we ignited them. Okay? Now, you are free to go back in the video and look at any point that you want and pause at any point that you want. I do also realize that the colors are going to be a little bit difficult to perceive. However, in this case, there is a correct answer because you're going to be asked to identify unknowns at the end of the flame test and match them with the colors. Be very careful with what you write down. And if you aren't sure, go back and look. Okay? Because I find a lot of students get these wrong. Like a lot more than I think should be necessary. Or appropriate, or whatever. If you are colorblind or have issues perceiving color, please, please, please ask people in the Discord for help. You are always allowed to start a conversation or a discussion and like, hey, I thought this was red. No, actually, I thought it was kind of orange because at the end, it looked like da-da-da-da-da-da-da. Like, please have that discussion, especially if you can't see the colors, if you can't discern them. I realize this is not a very accessible experiment from that perspective, particularly since you don't have a lab partner there to help you and say, oh yeah, that was blue, that was green. Okay, so that's part one. Part two is going to be more or less the same sort of thing where Samita goes through the experiment. If this will, it's rendering in 1080p because that's what I processed it. You're going to have a conductivity probe which records a conductivity on the screen. You're going to have to write these numbers down when the video directs you to and then draw conclusions from that. Okay, so that's the gist of experiment 3 is that video and then follow these directions as described on here. And then there's a bunch of questions at the end. Why did we do this? Why did you do that? Etc. Okay. That's really all I can think of for that lab experiment. I feel like this is a much simpler one than the density lab. Speaking of your density lab, I am still grading those. I've graded a few of them. I have like 40 left. My goal is to get through as many of those tonight as I can. But lab number 3 will be assigned tonight. It'll be due next week. So let me know if you have any questions. On the screen, I don't remember if we did this at the end of the period yesterday, but I'm going to give you a chance to do it today, right now anyway. So we were earlier, in an earlier slide, predicting what ionic compounds were based on their charge. So for instance, if I know that K becomes K plus and S becomes S2 minus, I could figure out what the formula is by balancing those charges. So what I want you to do is I want you to take these compounds and first predict what ion each thing forms. So for instance, I'm going to do this first one in terms of the prediction for you, and then put the ions together to make a balanced charge ionic compound. So in other words, how many positives, how many negatives do you need? Do they balance? How many of each ion do you need? So do that for all of those substances, and then we'll go over the answers. And then there's a second page that we're going to do in just a bit. So I'm going to give you like 3 or 4 minutes to try this. Remember, we're following the octet rule to figure out what an ion forms. All right, see you in a bit. One more minute, we'll go over the answers. All right, so let's go over the answers here. So I'm going to write down the ions that form and then the compound, because I'm going to work on the assumption that you know how to get to the ions from the octet rule. If you don't, let me know and I can explain that, though. So for this first one, I need to balance the positive and the negative, so I just get that. For the second one over here, for calcium and oxygen, the ion that forms for calcium is +2, and the ion that forms for oxygen is -2. And I need one of each of those to balance out the charge. For the third one, however, if I write down the ions and I put them together, what I find out is I get something like this. Like, my charges don't balance out completely, right? So that can't be the formula, MgCl. We got to put something else in here to balance out all of my charges. So I need extra minuses, so I'm going to just take a second chloride. And this balances out the charge for me. Same thing for this one. If I want to balance out the charge from sodium ions and nitride ions, I need extra positives from sodium to get that for my formula. How to get the ions? I'll do that in just a second. Let me finish this problem, though. So, and then for aluminum, I'm just writing out the answer here. And then I ran out of space there. And this works out because I have a total of +6 for my positive charge and -6 for my negative. So how do I get the ions? So if I go over to this screen, there we go. That's a little chaotic at the top, but that's okay. To get the ions for whatever we have, first write down your element symbol and draw its Lewis structure. So for example, if I had potassium, it's in group 1. I'm going to draw 1 valence electron. And then I need to get it to the octet, right? So I have to follow the octet rule, which for potassium would require me to do that. Get rid of its electrons so that it becomes this. Whereas something like sulfur, which has 6 valence electrons because it's in group 16, in order to make it an octet, I'd have to do this and this to it. And so that would become that. And so remember that an octet is always going to be 8, so getting all your 8 electrons. Or for metals and stuff, it's going to be removing all of their electrons. Because remember how we showed yesterday in this diagram. Oops, I clicked on the wrong thing. There we go. We showed in this diagram that if you can remove a layer of electrons, so if I get rid of this outer layer right here, then the previous layer becomes the octet. So removing electrons will also get you to an octet, but if you're already close, like all of these are close, I'm just going to add an extra electron for chlorine, bromine, and iodine. That will get you to the octet. Where am I on here? There we are. Can you count how many columns the element is away from the noble gases? For the most part, yes. But there are some elements that don't follow that pattern. And if I bring up P table, I will show you those. So for one, this would only work in groups 1 through 18, right? And so it's not difficult to say, okay, well, aluminum, how do I get to the nearest noble gas? I'm just going to count back 1, 2, 3, and there we go. So it should be aluminum plus 3. That does work. However, when you get to things like gallium, gallium also is plus 3 because it's in column 13. But if you do that same pattern, you end up doing this all the way back through the transition metals. And what you're supposed to actually do for gallium is you skip all of them and go 1, 2, 3. Which doesn't quite make sense at this level because I am hand-waving a little bit of what's going on here. We're going to address that in 161. But for our purposes, most of the time, you can just count how many columns away you are if you are either on the far left side of the periodic table or the far right. But that idea sort of breaks down for stuff that's at the bottom of column 3. All right, for more practice in balancing charges here, I want to give you these. Oops. So I'm going to give you 3 more minutes or so to try and make ionic compounds out of these ions. And we'll go over that answer when we get when I come back in just a minute. Would you like to share with the class, Maya? Maya? Hello? Maya says hello. We'll do 1 more minute and we'll go over the answers. Yeah, they love you. Say hi again. Now she's being shy. I would put her in front of the chat box, like physically put Maya on the desk so that she could like read the chat and then take a picture of it because I think that would be really cute. But that would require me to put her on my desk, and that is a precedent that I don't really wish to set with my cat. So she's just gonna have to hang out on the couch right here, which is like 2 inches away. Hi, yeah. No, you can't be on my lap. No, not right now. I gotta put you on the blanket here. There you go. She immediately comes right back. All right, so for these two ions, I need to balance them out so that the total charge is 0, and I can do that by adding a second one of these. Maya, that so Maya is now just going to rub against my arm. I have one arm on the armrest, like holding the tablet in place, and she is now brushing against it with her whiskers, and I'm ticklish, I guess. So if I start giggling, it's because of the goddamn cat. Maya, stop. For this one, what about the silly 7 elements? Do those count in ionic compounds? We're not going to use them in their diatomic state, so I'm not sure what you mean. So, like, the silly 7 would be covalent compounds. But the elements can also be used in ionic compounds. So I'm not quite sure what you mean specifically by those compounds. For aluminum and sulfur, if I do this, this is going to get me to have 6 of each positive and negative. So the ionic compound that I would form would be that. And I don't know why I keep doing this example over and over and over and over again. Like, we've done this like 74 times, and I just keep picking it, so. Yeah, don't worry about the ones in the diatomic state, because those are not ionic. Those are covalent. So we've done those 3. I'm going to hit clear, and then we'll do the last 2 here. So I've got these now, and because 2 and 4 are related by a factor of 2, I can easily do this and say, okay, that's going to be all I need. And then look at my charges to make sure that I have the same amount of each, and I do. This one down here, there is no common denominator, though, so I basically have to do the back and forth thing. So I need more negative. Now I need more positive. Now I need more negative. Still need more negative. And so I end up getting 15 positives and 15 negatives for that. Now, in most cases, you can just swap the places of these and say, okay, well, if one of them is 3, if one's 3 minus and one is 5 plus, I'm going to have a 3 and a 5 in my formula, and I'll just swap them. However, that doesn't always work, because you could see up here that this didn't actually pan out, right? So if you have a common factor involved, it needs to get divided out if you do this swip-swap sort of thing. So Maya's making me think that I haven't fed her or something, so I'll check that out in the break, I guess. But for now, let's keep going. Let me know if you have any questions. All right. Now, when you are making a formula out of ions, you're going to balance out all the charges. That's pretty straightforward. But what happens if I give you the formula and I want you to work backwards? The answer is, well, you know what all the ions are from the elements that come from groups 1, 2, or 13 through 18. For example, cesium is in group 1, so it must form this ion. And arsenic is in group 5, so it must form this ion. So that's something that you can do. That's very straightforward for a compound like this. Even though it looks unfamiliar, you can deduce that very quickly from seeing where the elements are on the periodic table. Now, in the event that you have a transition metal, you cannot do that with a transition metal. You have to solve for it instead. And so what you have to do is you have to use the other ions in the equation, or the formula, to figure out what the metal must be. So for example, let's look at this. So I don't know what tin is. All I know is that it's positive, because it's a metal, right? But I do know that I have two oxygens, and oxygen in an ionic compound is always going to be this. So what must this be? Well, if the total negative and the total positive are equal in an ionic compound, you now know what it must be. Oops, I didn't think there'd be that much text there. So in ionic compounds that have a transition metal or one of these lower group 3, 4, or 5 metals, like bismuth or tin or lead or whatever, you have to solve for what the charge is, because it doesn't fall in a group that has a consistent number. All right, so what I want you to do is, for each of these compounds, I'm going to number them here. 1, 2, 3, 4, 5, 6. What I want you to do is figure out what all of the ions are in them. For some of them, that's going to be trivial because they contain only elements that follow the octet rule. But others contain transition metals, and you're going to have to solve for them using the other ions that are present. Okay? Go ahead and try that, and write out their ions in the chat. I'm going to go see if Maya needs food, because she still hasn't gone away. Normally she's like 5 minutes, and then that's it. I'm good for an hour or two. So I'm going to check on the cats, and I'll be right back. One more minute, we'll go over the answers here. All right, let's go over the answers here. So for the really simple ones, I'm just going to write out the answer immediately because these follow the octet rule. So that's no problem. I thought one of these down here did, but it doesn't. Now for the other ones down here, we have transition metals. So we have osmium, rhenium, gold, and scandium. So we need to solve for these. And the way that we do that is to just write out all the ions that you know. So I don't know what osmium is, so I'm going to just leave it blank for now. But I know that I have 4 oxide ions here. For a total of 8 minus, because oxygen always forms a -2 ion, right? Which means that osmium must be +8. And it totally is. And you might think, holy crap, I thought elements went the shortest direction to get to the octet. Why am I taking away 8? And it turns out transition metals, again, don't follow the octet rule. And yet, even with that in mind, this is the shortest route. Believe it or not. So that's osmium for you, so. Alright, we do the same thing with rhenium here. Don't know what it is, but I have 7 of these Cl minuses. Which I'm just going to write like that, times 7. So that means that rhenium must be this. And there you go. Alright, I do have to hit clear here real quick, so. I got rid of the numbers, that's alright. Oops, that's not the pen tool. That's just click on the thing. Alright. With gold, I have 2 of them. And I don't know what charge either of them is, and I have a single oxygen. So I do the same process. So here's my negative. That means my total positive must be this. But now I have to split this among 2, right? So each one must be +1. That's how we would get to that one. And then the same thing for scandium here. So I got 3 scandiums. And I got 2 nitrogens. And I know that charge on nitrogen is -3. So that means that the total positive charge must be +6 to counteract the -6 from the nitrogens. And now I have to split that 3 ways. There's only one way to do that. For any problem I give you, all of the ions will have, like all of the same ion will have the same charge. So I'm not going to have a mixture of scandium 2 pluses and 3 pluses in the same compound. I'm not going to give you something like that. Those ions actually do exist. For example, I believe that there are things where there's iron 3s and 4s in it. But those are complex, and we're not going to encounter those in Chem 140, or even Gen Chem at all. They're very rare. Alright, if you have any questions about how to make ions or follow the octet rule or whatever, let me know. The last thing we're going to do when forming forming ionic compounds is we're going to use polyatomic ions, because this is part and parcel of the whole ionic compound is polyatomic ions are just bigger ions. Now, The list of polyatomic ions I gave to you at the start of Unit 6, and you probably don't remember them because, again, online class, right? Don't commit shit to memory you don't need to. You only have so much brain hard drive space. Although I personally think they're important, there are better things to worry about during a pandemic, right? So if you have the Unit 6 slides downloaded, go and open those up. They're on the first slide because we're going to start asking questions about them here. And those are going to be questions like, oops, I don't know why that went backwards. What ionic compound is made out of these ions? And the rules that you follow are exactly the same. If this is the charge of this ion and this is the charge of this ion, I'm going to just stack them together until I have a total charge of 0. And once I do, I can then just put everything together. So I have 3 calciums here and 2 phosphates. So this would be the formula of your ionic compound. Note that the parentheses are required. If you don't have parentheses for a polyatomic ion, then what ends up looking like, it looks like I have 42 oxygens now, and that's very obviously wrong. So you should get something like that. All right. So what I want you to do is I want you to combine these ions to make ionic compounds, and then I want you to break them apart. Combining them is way easier because you can see the charges, but down at the bottom, I have thrown some polyatomic ions in there that you don't know the charges necessarily if you haven't memorized them. So you're going to need to go back and look at Unit 6. For those polyatomic ions and their charges, because you're going to treat these as knowns, just like you know what chlorine's charge is, because you can follow the octet rule. You know what cyanide's charge is, because it's on a chart that you can look up. Okay? So write the formula of the top 4, and then split the bottom 4 compounds into their ions. Give you about 4 minutes to do it, and then it'll probably be break time. So I'll see you in a bit. one more minute. We'll go over the answers here. All right, let's go over the answers here. Is this... I gotta clear my thing here. We'll just go up here. All right, so write the formula for these combinations of ions. I don't really have much space, so I'm going to use this screen to do it. All right, so I've got my barium, and I've got cyanide, and I just need to balance out the charges here so that everything is the same. So this is 2 plus and this is 2 minus. And we get bacon. No, that's not how you make bacon. Bacon does not have cyanide in it. But you know what does have cyanide in it? Almonds. That's actually... Cyanide tastes like the almondy flavor, is what I have been told. I'm like 85 to 90% confident that that's true. I've never personally tasted a chemical like that had cyanide in it because it's toxic. So don't do that. All right, we got this and we got chromate. And so you got to do the same thing. Balance out those charges, right? If you aren't sure if you have enough, just draw the line down there and balance out the charges and see what you can do. Wow, that was a terrible letter O. Let's try that again. There we go. Don't need parentheses there because I only have one of the polyatomic ion. If I put parentheses around this, it doesn't really help any, does it? So now I got to go back over to the history and delete those 2 brush strokes. There we go. All right, and then we got ammonium and sulfate. And I have 1 positive and 2 negatives, so I need another positive to balance that out. Let's just double check. 2 plus, 2 minus. Looks good. My O there looks a little bit lowercase. I don't want that. I want this to be capital. There we go. And then finally, aluminum and hydroxide here. I must have 3 extra, or 3 total hydroxides to make that work. And there you go. There we go. Okay, so now for the next part, we're going to split these into ions, which we're going to do more or less the same process, but backwards. So I have strontium, and I don't know what ion it forms, but I do have carbonate, and if I look up carbonate, it's this. So strontium must be this. Is it still correct with parentheses? So if you don't need parentheses, but you put them in anyway, Canvas will mark it wrong. Other people would identify what you are doing, but Canvas is looking for a specific combination of letters and numbers in a certain order. And putting in extra parentheses kind of screws that up. So, like, for example, if I had, like, this... For example, this compound would make sense, but technically so would this or this, right? Like, the parentheses don't really imply anything, but I can only make canvas accept one input. And so the input that I have it accept is this one, where I have this 2 here. So if you don't need parentheses, don't put them in. On paper, you can do whatever you want to, but as general practice, only include the parentheses if you need to. We got iron with I don't know charge, and cyanide, which is minus, and I got 3 of those. So total 3 minus, this must be 3 plus, this must be 3 plus. All right. Finally, we have 2 more, actually. So I got potassium. Potassium, we actually know what potassium is, so that one's easy. And then sulfite, we know what that is when we look it up on the table. So this one's just done. I'm not really sure why I threw that one in there. Probably to keep you on your toes. I don't know. And then this last one, we got to play with vanadium again. Vanadium is always weird. But I've got a bunch of phosphates. I've got 5 of these. So I go down here. Oh, I have a bunch of vanadiums too, so VVV. There you go. So if I have 3, 6, 9, 12, 15 minus, I must also have 15 plus, and I have to split that 3 ways. So each of these must be 5 plus. Now you might notice I'm giving you a lot of vanadiums that are plus 5, and you might think, oh, well, vanadium is just plus 5. There are other vanadium ions possible, but 5 is the most common one. So that's why it keeps popping up. 2 is also common. I think 3 is a little less common. I don't know about 4. This is literally my degree in organic chemistry, so I should probably know more ionization states of vanadium off the top of my head, but all I know is vanadium is very colorful, and if you look on YouTube and you look like vanadium ion, I believe is what it's called, but vanadium oxidation states and colors, like you can get almost the entire rainbow of colors from just vanadium. It's real pretty. All right. That's it for this section. When we come back from the break, what we're going to do is we are going to learn how to differentiate between ionic and covalent compounds, which is going to be our segue into Unit 10. So we'll do that in just a little bit. Let me see if I can find the next song here. Yeah, there it is. All right. See ya in a little bit.
し輝いて重なり合う奇跡を描き続け形がいよ
憧れのビューティフォースター回るディスコボールやってきましたディスコホール目指せ輝くナンバーワン望みは高く限りなくオラのダンステップにみんなハンズアップフロアのテンションはもうライザークラップハンダベヨースタンドアッパー集まってそう固まってヒアウィゴーだエブリバディレーザービームでレッツラゴー上り詰めるべディスコプリンス宇宙に届けこのディスコダンスみんな大好き I love you ディスコゼックそうファンキーナイMIC でチェコワンズオラの話も一遍聞いてくれ熱い魂語るライムスターそうやってきましたアイマスター夢は輝くナンバーワンきっと届くべなてめねこの思いラップテックにみんなハンズアップフロアのテンションはもうライザークラッペハンダベヨースタンドアップ滑舌は確実そう格別ヒアウィゴーだエブリバディチェケラッチョーでレッツラゴー上の方目指す方法集めて固めてそして語るべみんな大好き I love youしてそう集めれば星になるいつか To the sky 誰だって飛べるのさ夜空を走る王様レイの金色に見え I change my life 夏の虹めがけて To the sky 必ず見つけるよ憧れのビューティフルスター 友達に紹介すっからな魂回すよ DJ やつのプレイはそう GJ ナンバーワンやつのスピンナップにみんなハンズアップフロアのテンションはもうライズアップクラッペハンダベヨスタンダップまとまってそうくっついてキュッキュッキューのパッパッパテカテカテカテカテカみんな大好き I love you ディスコテック so funky nightしてそう集めれば星になるいつか To the sky 誰だって飛べるのさ夜空を走る王様レインボー君の耳へ愛地にまら夏の虹めがけて To the sky 必ず見つけるよ憧れの beautiful star
Oh, it's so catchy. I don't know what it is about this music. Let's pan that away. And let's keep going. All right, so what are we going to do next? So, that's right. I just told you about this. So, this is just a little segue section that will connect Unit 9 and 10, because Unit 10 is Covalent Compounds. What I'm going to introduce to you are a bunch of properties that describe both of them, and we're going to sort of gloss over the covalent compound stuff for for this 5 minutes, and then when I open up the slides for Unit 10 in just a little bit, we'll see what those properties actually mean. So, on the left in blue, I have all my ionic compounds. So, ionic compounds form formula units. If I haven't described that already, we're going to see a picture of that on the next slide. I'm pretty sure I've shown you a lattice, but we'll see. We have already discussed how you transfer electrons from one atom to another to form the charges, and that they form between metals and nonmetals. And then I have an extra little note or caveat coming up on the next slide. Covalent compounds do virtually what I would call the opposite of these things, although opposite may be the wrong word in some cases. So, for instance, molecules are individual discrete entities, whereas formula units are just parts of a giant lattice. Covalent compounds share electrons, which means that they aren't transferred. There's no charges in covalent compounds. And then finally, only nonmetals are involved in covalent compounds. Now, there is a weird exception that we're going to have to note right here. And that exception is NH4 is going to screw everything up. So be very careful about when you see this combination written like this. Because, and I'm going to highlight the word ion next to it, this is an ion. It only has nonmetals in it, but it's still a polyatomic ion, so it forms ionic compounds. So all of these compounds down here are ionic, even though there are no metals present, because NH4 plus should be treated for the purposes of compounds as a metal, in terms of is it ionic or not. Now, as you get further and further in chemistry, the metal-nonmetal distinction for ionic compounds and covalent compounds is going to kind of fade away. We're going to trade it out for a property called electronegativity, which we'll talk about in 161. But for now, this is good enough. Look for a metal or ammonium. If you see that, it's an ionic compound for our purposes. That'll be good enough. All right. So what I want you to do is I want you to categorize each of these as either ionic or covalent. So I'm going to write down a bunch of numbers, and so you can just write in the chat, oh, 1, 2, 3, 4, and 7 are ionic, or whatever. So you don't have to go 1 ionic, 2 covalent, and then on and on and on. So based on that description, type in the chat which ones are ionic and which ones are covalent. And you should be able to do that in like 2 minutes. So we'll check back in just a moment. All right, let's go over the answers here. So I'm going to just highlight all the metals here. So we got silver, and we've got potassium, and iron, and platinum. And then you notice in the chat, oh, hold on, I gotta ban spam bots here. No, not pin message. That's the opposite of what I want to do. There we go. Get rid of that. Hopefully that doesn't stay there forever. No, I do not want to pin this. Unpin this message. God. Yes, please don't click on any of those random shit links that pop up. Okay. Hopefully that will go away. I will look at that later. But yeah, you also just notice that, like, wait a second, NH4 is in there, and you'll notice that I conveniently also put in NH3, which is totally covalent because it's not NH4. So be very careful is really what I'm trying to say here. So yeah, the ones that I've highlighted in yellow have metals, and thus are my ionic. So, oops, that's the wrong pen. So 1, 5, 6, 7, and 8 are ionic. And then 2, 3, and 4 are covalent. All right, I believe that's everything. And I gotta do this so we can have our hooray. There we go. All right, screen will go black for just a second while I load in the slides for Unit 10. So give me just a second here. Oops, what did I just do? Oh, I've broken everything. There we go. All right, there we go. It's on the screen now. I forget where the next quiz falls. I believe it's 9 and 10, but I'm going to have to check. Unit 10 is very, very short. I don't really cover much of the stuff from Unit 10, and also I don't believe there's that much in the workbook. Really, what we're going to be doing is just simple Lewis structures for covalent compounds, so that you have a general idea of what they look like. Will we finish this today? Probably not. Okay. How much time do we have? Maybe we will finish this today. I don't actually know. Well, let's get started and see how far we get. So, a covalent compound is a compound that is fundamentally different in terms of its properties than an ionic compound. So, for example, ionic compounds have super high melting points. You have to heat table salts to, like, I want to say it's like 800 Celsius to get it to turn into a liquid. You have to heat it up real hot. Like, you cannot do this on your stovetop. It won't go that high. You just dissipate too much heat. But water, on the other hand, you only have to heat it to 32 Fahrenheit or 0 Celsius to get it to melt. So that's very low comparatively. And a lot of covalent compounds are like this. For example, gasoline is a liquid at room temperature. So is butane's actually a gas at room temperature. Butane's only a liquid because it's pressurized. But propane that you use in your barbecue, or maybe your various propane accessories. I'm trying to tie King of the Hill in here because my streaming group is on a King of the Hill kick. Those are all examples of covalent compounds. They have very low melting and boiling points. The gases that we are breathing, so like oxygen and nitrogen and water vapor and carbon dioxide gas, those are all covalent compounds. Now, the ones that are in the solid state at room temperature, like sugar or wax, tend to have very interesting structural properties. For instance, if you grind up sugar into a fine powder, you get powdered sugar, and it's very, 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 very soft and fine. However, if you try and do that with table salt, you can get like popcorn salt, which can be fine, but it's still a little crunchy to it. And the reason for that is because crystalline compounds like table salt will stay crystalline no matter how much you grind them up. And in fact, it's very difficult to grind them up to a point where they are extremely fine because the ionic bonds in crystalline compounds such as table salt hold them together into crystals fairly effectively. Sugar isn't held together that way, and so you can get individual molecules to separate apart with enough effort. Obviously not like to our senses. You can't taste a molecule of sugar, but you can certainly get very, very, very fine stuff that our senses can't discern. And then you have stuff like wax, and it's like, where the heck is the molecule for wax? It's just like a glop. It's a soft solid, right? Like, what do you do with that? So these compounds must be totally different. And it turns out that the bonding in these compounds is different, and how they interact with stuff around them is also unique. We're going to talk more about how to interact with stuff around it next quarter in 161 when we talk about intermolecular forces. For now, we're going to just focus on the bonding. And the bonding is different. And we're going to show that in here. Now, how is the bonding different? The examples that I'm going to give you are going to be very, very obvious at first because I've selected them that way. But the necessity of our bond is that the valence electrons that are involved can't be transferred. They have to be shared instead. And here is why that works out. So we're going to look at F2, which I'm going to get rid of this text. I'm going to quickly draw the Lewis structure of F2. And we're going to see that if I try and take an ionic approach to this, I get stuck real quick. So if I want to move an electron over like this, then the atom on the left is farther away from the octet than when it started, because it started with 7 valence electrons, and giving an electron away gives it 6. That's no good. The atom on the right would be satisfied. It would have an octet if I transferred one electron from the left to the right here. But there is no mechanism by which I can transfer an electron from one atom to the other and get both of them to have an octet. There just aren't enough electrons available. I need to have some factor of 8, right? And here I have 14, so I'm kind of stuck. So I can't do this. I have to do something different. And what we're going to do is this. We're going to slide them together. And the ones that are in the center are going to count for this left atom, but they're also going to count for this right atom. So what we're basically doing is cheating. I don't have enough electrons to give everyone an octet unless I double count them. So that's what I'm going to do. The electrons that are double counted are my shared electrons. So in this way, I can get 8 valence electrons by sharing a few of them. Now, something to note is that the electrons that were shared were the unpaired electrons. Those electrons are the ones that eventually share together, because they provide a space for the other incoming electron to slot into, for example. We can get rid of this now. So this bond that we have formed is the covalent bond. Covalent meaning co as in communal, we're sharing the electrons between atoms, and valent as in valence electrons. So that's where covalent comes from. All right, and so again, if I circle these, everyone has an octet because the atoms think they have the electrons. As far as they are concerned, the electrons are close to each atom at all given times, and thus can be counted as part of their octet. So the atom or the molecule is stabilized by that. Now, because they want to have their octets, if one atom in the molecule moves, the other one has to tag along with it, because the attraction of these electrons, I'm going to just draw these electrons like this. So these are these electrons right here. The fluorine has a nucleus which has 9 positives in it, right? And so there is attraction from the nucleus to each of these electrons. And that attraction from the electrons is also attracted to the nucleus. So they kind of stick together. Yeah, they're kind of like Legos. That's a good analogy. They'd be like 2 Legos that stick together, but then can't stick to any other thing. You know, the impossible to separate really thin ones, but on the top it's like smooth because it's the top of something. I don't know. All right, and so this is our covalent bond. The covalent bond occurs between the shared electrons. So again, there's a covalent bond. Now, the format for drawing covalent bonds is not to draw these 2 dots in the middle. This is just for theory. What we're instead going to do is we're going to replace any dots that are shared between atoms with a line. Every time you share 2 electrons, we're going to draw a line there. That's going to be our single bond. If you were to share more than 2 electrons between 2 atoms, say 4 or 6, you would draw more lines, and so you'd get a single, double, or triple bond. So let's look at some examples of that in a second. Oh, the other thing I want to mention is that there is a name for these electron pairs on the outside, so I'll just circle these. Electrons that do not participate in bonding, we refer to as non-bonding pairs. That's going to be relevant in 161 when we talk about shapes of molecules, because those electrons do occupy space, they repel other electrons, and will thus dictate the geometry around a given atom within a molecule. But for our purposes, any two electrons that are paired together don't participate in bonding. All right. So whenever you are drawing these structures, you're going to basically take your unpaired electrons and use them to form bonds. When you connect two of them, use a line to represent that. And that's going to be your bond. When you go back and check on your molecule at the end, when you do something like this, you're going to want to check to... Oh, that was a terrible circle. I just want to circle one thing here. When you go back to check your molecule, hey, does this have an octet? And you're counting electrons, because everything has to have an octet, right? That's the whole aim of the game. You're going to count 1, 2, 3, 4, 5, 6, and then the bonds are going to count as 2, because those electrons are shared. And you get to count it for 2 for both sides. Now, hydrogen is kind of weird. Hydrogen only has 1 electron because it's tiny, and if it bonds to something, and you check how many electrons it has, it'll just have these 2 from its bond. That's totally okay. Hydrogen is ambitious enough only to become a noble gas configuration like helium has, which would be 2 electrons. If hydrogen can just get 1 more electron, it's fine. All right. Now, the next thing that we're going to try and do is we're going to try and share multiple electrons between 2 atoms to get more than 1 bond to satisfy the octet rule. And so that's going to look like this. So for oxygen, if I draw oxygen on the board for its Lewis structure, I could say, okay, well, this electron could go in this spot right there, and this electron could go in this spot right there. And then I could draw this around it, and I have a frog. Maybe it doesn't really look like a frog. It totally looks like a frog when I do this on the whiteboard, but that actually looks kind of hideous and awful. So we'll just pretend that that didn't happen. We'll just do this. There's our shares. And so we're going to share those. That's going to look like this. And then, for each instance of a pair of electrons, I'm going to replace it with a line. And that's going to look like that. All right. So this would be a double bond. What I'm going to have you do now is I'm going to have you draw this Lewis structure without any input from me, and I want you to tell me how many bonds you make. I'll give you a hint, it'll be more than 1. So I'm going to have you draw nitrogen, N2. I'll give you like 2 minutes to do it. Tell me what type of bond you make in the chat. All right, 1 more minute to finish the structure, and we'll go over the answer. All right, let's draw the Lewis structure. Actually, you know what I'm going to do? I'm going to draw it on this one because I know that I have a bunch of text coming up that I'm going to overwrite this. So let me erase all of this. So I'm going to draw the Lewis structure for nitrogen. I'm going to draw another Lewis structure for nitrogen. And then I'm going to just connect the dots here. So I'm going to connect these three, or these two, and these two. So I'm going to pair up those, and then the result that I'm going to get is going to look like this. And we create a triple bond. Oops. All right. So we'll go back over here. Now, is there a systematic approach to the number of bonds formed? Generally speaking, yes, but there are so many exceptions to what I'm going to show you here. So use this sparingly. So there's a rule that I noticed that was in your notebook or the workbook that says something like this. 8 minus the group number is the number of bonds that form. This usually works. However, it becomes a little less reliable the further down this chart you go. So, for instance, this is pretty much always valid, but this and these are a little bit most of the time. So, I don't really like this rule because later on we're going to get to stuff where you start seeing things like this, and this is valid. But then when you look at that, you're like, well, wait a second, that only made 1 bond. I thought it should make 2. Yeah, it should make 2, but it doesn't always. So just be mindful that this is a suggestion and not a hard and fast rule. Now, what is the maximum number of bonds that you can put between atoms? Because this is just suggesting the number of bonds that can go from the atom. I'm going to call that the central atom. So these are not necessarily going towards one atom. So for example, oxygen could make a double bond to something, or instead it could just make 2 single bonds to something. Both of those are allowed. Those single bonds would just go to separate things, and so you'd have 3 atoms in your molecule if that was it. Likewise, carbon can do something like this. It can have bonds going all 4 ways. It could have a double bond somewhere. It could have 2 double bonds. It could have a single bond and a triple bond. But can it do this? It turns out this one's not okay. And the reason for that, we'll draw on this screen. If I draw out my Lewis structure like this, and I try and connect the dots, like so, I can't draw a straight line to connect my electrons. They're on opposite sides, right? Turns out that bonds form in straight lines. You can't make a curved bond. So I can only make at most 3 bonds. Between atoms. And for the purposes of this class, that will be true. Can I make a 4th bond to something? Turns out that there are things that do that, and guess what they are? They're metals! Because chemistry is weird. When you get to the higher level stuff, all these patterns we're making fall apart. Yeah, metals can totally make multiple covalent bonds beyond 3. Rhenium can make 7 covalent bonds. What the fuck, right? Like, why is that a thing that can happen? And it turns out it has to do with electrons, but it's well beyond the scope of anything that we've covered so far. So for our purposes, this is going to be true. At most 3 bonds between atoms. So what this would look like is I'd have a dot here. Here's my triple bond. And I have a dot here. And these could go bond to some other thing. Like, say, a hydrogen or an oxygen that needs to make a bond or whatever. Okay? So, at most 3 bonds between 2 atoms. But the remaining bonds can go any which way that they want to. Alright. And again, later on in Chem 161, we're going to break all these rules. We're going to break the octet rule even. The octet rule, which has been our cornerstone for bonding, we're just going to say, like, yep, we don't need this anymore. And it'll be fine. So what I want you to do, and this will be the last thing we do today. We'll stop a little bit early because the next section takes more than 10 minutes. I want you to try and draw the Lewis structures of these using this dot approach. So draw out the simple structure of each atom, and then try and connect the dots. And see if you can create something that fulfills the octet of everything and also pairs all the unpaireds to make bonds. Okay? So I have 6 molecules for you to try. I'm going to give you 6 or 7 minutes to do this. Then we'll go over the answers and we'll be done. So see you in a bit. All right, obviously you can't put these in the chat, but we'll do 1 or 2 more minutes and then I'll go over the answers. All right, let's go over the answers here. I'm going to run out of space if I work on this sheet, so I'm going to just work over here. Did I select all? I did. And I can do this. We'll just work on this side of the page. There we go. Okay, so for Cl2, Cl2 is basically just like F2. So there's a Cl. There's a Cl, and I'm just going to connect the dots. And then we'll tidy up. So when I say tidy up, what I mean is I'm going to make my bonds straight lines. So there's my Cl2. And then for BRF, exactly the same thing, because I'm just picking things that have 7 electrons. And really, I could just put anything that's in column 17 in these spots. There you go. Now for CF4, we have to do a little bit more work here. So I'm going to put my C down here. And then I have a bunch of F's here. Oops. That was a mistake. Sorry, hold on. Let me fix that. So 1 on each side, and then we'll start pairing them. And I'm just putting the unpaired one towards the carbon, because that's eventually where I'm going to make my bond. And I ran out of space. I gotta keep scrolling. All right, I'm gonna draw these in blue before we tidy up. So I'm gonna connect these two, and these two, and these two, and these two. So these are all gonna get shared. I'm indicating sharing with my double arrow here. However, I need to tidy this up because bonds have to go in straight lines. So what I'm going to end up doing is I'm going to do something that looks like that, and then I'll put the fluorines around it. And then that's going to look much better in terms of what the molecule structure is like. Later on, what we're going to learn is that because electrons live in these bonds and electrons repel, they have to be as far apart as possible, and they make an angle. But that angle actually isn't 90 degrees. For now, this is fine. But when we get to 161, again, we're going to look at geometry and how a tetrahedron is the optimal arrangement. So for now, writing it at like all 90-degree angles, that's okay. All right, we got H2O, so here's my oxygen. And I got 2 hydrogens. And we'll do the same thing. We'll make these share and these share. And then we'll tidy up. And there's what water looks like. Water is a very angular molecule. Now, if you drew water like this instead, Also okay. For the purposes of this class, that's totally fine. All that matters is that you have 2 unpaireds and 2 bonds for a total of 8 electrons around your water. All right. OF2 is the same molecule in terms of its structure. I should have dotted that correctly, sorry. There we go. So it's going to look exactly the same as water. And let's tidy up. You'll notice that I'm not doing one per side when I tidy up. And that's because I've already done all the connectivity and I know everything worked out, so I'm just filling in the electrons. So there's my OF2. And then finally, C2H4. This is where our blueprint kind of starts to fall apart here. So this connect the dots method is real good for simple molecules, but when you get to more complex stuff, it doesn't work super well. So for instance, if I did this, and I've already screwed that up. Hold on. If I did something like this, and that, and that, and then maybe that, then what I end up having to do is I have to share something between these 2 carbons, and then I have 2 that are that are unpaired. I can't do that, right? So this didn't work. So this strategy led to having unpaired electrons that I can't just force together. So I have to undo. Undo, undo, undo. There we go. Now, if you try this enough, you'll eventually see that... Oh, I've already screwed it up. You'll eventually see that I've screwed it up. You'll eventually see that there's really only one way to make this work, and that is to pair 2 on each. And then I can pair these together on carbon. And then I can tidy up. So my carbons are double bonded together, and then each of those has a hydrogen, or 2 hydrogens, sticking off of it. So that's the correct structure, but this is kind of just a, oops, this is just kind of a mess. This is supposed to be like my frustration symbol there. And so we need to devise a better way to draw Lewis structures, rather than use this connect the dots approach that as our molecules get more and more complex is going to get more and more frustrating. And so when we come back on Monday next week, we are going to discuss that in more detail. But that's all the time that we have for today. I do want to thank everyone for coming out to the lecture. Make sure that you get quiz number 4 done soon. It's due tonight and closes tomorrow. Lab number 3's assignment will go up after class today. I need to go get a little bit of food, and then I will get all of that programmed online. But other than that, that's all I got. Let me know if you have any questions in the Discord or email. Have a wonderful weekend. Take care.